Okay, welcome everyone to day number 2. Let's take a quick mental review of day number 1. Question: what is a stochastic program? Anybody? If you had to summarize it in one sentence, what would you say? Yes.
Going to be a program where some information are unknown at first. We are going to take decisions without knowing this information, and then when they are available, we are going to update our decisions.
Okay, good summary. There's uncertainty and there's decisions that have to be made. Perfect. That's a perfect starting place. Now I want to do something that may seem odd at first. I need 2 people who speak some other language than English, which is probably most of you. And I want you to come up and I'm going to have you write a sentence on the board in your native language. So, Tuğçe, I met you last night. I assume you speak Turkish. Could I ask you? And Charlotte, I know you speak German. So, okay. Yes, come to the front. Watch out for the cables. There's a hazard up there.
Feels like a vocabulary test in Latin classes.
Vocabulary is in fact the perfect word. So I want you to listen.
You told me to write it. Where? In the middle?
Up high and then
Up high.
okay. Okay. This question is for people who do not speak German or Turkish. What do you think this says?
I love optimization.
Okay, that was a very fairly easy guess, I suppose. I love optimization. Definitely, these are 2 different ways of writing the same thing. Would you agree? I could write it in English. We could write it in many languages. What am I trying to say? Yesterday, you learned one way to talk about uncertainty and decisions. Today, you're going to learn essentially a different vocabulary to do exactly the same thing. And on day 3, we will illustrate to you that they are in fact 2 different vocabularies to say exactly the same thing. Why do we have different vocabularies? Well, why do we have different languages? Why do we talk about the same thing in different ways? It's because we approach the same topic from different perspectives. And so we end up with different dialects, different ways of saying the same thing. And that's okay. As students, you will benefit from learning as many of these as you can. Probably you may specialize in one, but to be unfamiliar with the others, that's probably myopic. Myopic is a good vocabulary word for today as well. So put that in the back burner. Does everybody have a handout? Okay. So I've prepared this for you to help you take some notes and to break up this slide versus trying to take notes. And I find this to be an effective way to learn. I hope you find it to be that as well. Thank you, Charlotte. Tuğçe. So let's jump in. We're going to start on page 1. And I will read the parts that are printed and we will fill in the blanks as we go along. So section 1 is all about modeling. This is about how to model a stochastic dynamic program. A stochastic dynamic program is a model of an optimization problem that consists of the sequence decision, information, decision, information, decision. Where did the stack of handouts go? I'm sorry. Are there any left? Okay, can I have one, please? One more. Okay, we're going to talk about a particular type of stochastic dynamic program called a Markov decision process. Now, from yesterday, I gather that many of you are familiar with these sorts of things already. Some of you probably are not. So I'm going to treat this as if you are not. We're going to start from square one. So a Markov decision process is a type of dynamic program. It consists of, and we have a number of things here. First, decision epochs. This is the point in time or a stage at which decisions are made. Next, we have states. Here's the definition of a state. It's all the information you need to define feasible actions, the reward for choosing an action, and the transition. Of course, we haven't defined any of these things yet. So if you're truly starting from square one, this definition is of no help, but we will get there. Next, we have actions. These are decisions available to you from a particular state of your process. Next, we have random information. Random information is exactly what it sounds like, possible realizations of uncertainty, and we need to assign probability distributions to these realizations or likelihoods. Next is contributions. This is an expected reward or cost incurred by choosing an action in a given state. We're almost finished. Keep with me. Transition function. Transition is some function that says how my state variable evolves. Yes. Sorry, say it again.
Oh, no, given.
Given state. I'll try to write better. Okay, and finally, we have an objective. Every good optimization problem has an objective. The objective typically is an expected value of the sum of your contributions. The expectation is taken across random trajectories of states. And the random trajectories of states are transformations of your random information with respect to the transition function. Are you able to see this? Am I writing big enough in the back? All right. Okay, these are the modeling elements. How does the process actually proceed? So I've listed some bullet points on your worksheet. Let's go over this. First, decisions are made at each epoch. I'm going to index them by 0, 1, all the way to capital K. You might make a note that capital K could be a random variable. In other words, it may not be known ahead of time how many epochs there will be. At epoch little k, the system occupies some state, we'll call it Sk. In state Sk, we choose action Xk from the set of feasible actions. So we're going to have some set that says, in this state, here are the choices that are available to you. The expected contribution accrued is capital Ck, which is a function of your state Sk and action Xk. A realization of random information is observed. We'll call this Wk plus 1. The transition to Sk plus 1 is made. So I've notated this as a function capital S. It takes as input your state, your action, the information, that it moves you to the next state in the system. We begin at an initial state, call it S0, and you repeat this process until you reach some terminal state, S capital K. So at every epoch, it's the same. You're in a state, you select an action, you observe information, you transition to the next state, repeat. The optimization proceeds as follows. A policy is a sequence of decision rules. We're going to use pi to represent a policy. And a sequence of decision rules, you see the capital X, it's superscripted by pi, subscripted by the epoch. Each of these is a function or a decision rule that maps your current state to an action in the feasible action set. So if you're familiar so far with maybe more classical forms of optimization, say linear programming, math programming, typically in those paradigms, we have a decision vector call it X. And then we choose X from some set. Here, our optimization is not across vectors, it's across a space of functions. We call them decision rules, and the sequence of decision rules is what we call a policy. Now, in two-stage stochastic programming you learned yesterday, it's essentially the same thing. The first stage, you could think of more as a vector, but that second stage choice is a function of the information you observe. So in that way, it's exactly the same as what I just described to you in the context of a Markov decision process. Okay, we're going to denote the set of all policies as capital Pi. And then finally, the objective is to optimize the total expected contribution, conditional on the initial state. Okay, commit that to memory, that objective formation. Maximize expected value of the sum. We're going to come back to that. All of this, though, can be represented, in my opinion, much more succinctly as a picture. So let's do that now. I'm going to draw a picture of a decision tree. Yes.
I have a question about the notation. What is small x pi of sk
Where is that?
in the objective function?
Oh, that's a typo. There's supposed to be that's typo number 1. We'll see how many we find today. That should be a capital X pi with a subscript K. Yeah, could everyone make that correction? So in the objective, it should be, that should be a capital like this.
And then follow-up question.
Yes.
And then in the bullet where we define capital XK pi, is this mapping to a single decision or to a set of decision options? Because with the
Right.
mathcal x of sk, this.
So I've defined the function as mapping somewhere to that set, but if we consider what we call deterministic policies,
Yeah.
It's going to map to a single action.
Yes.
If you have a randomized policy, then there could be several actions that get mapped to. But
Okay.
we're not going to consider this.
Okay.
Good question. Others? Yes.
For the immediate contributions, you don't consider the realization, right? Just
Say it again. Don't
the
consider what?
immediate contributions are only based on the state and the action I take, and not the result of the action.
Hold that thought for just a moment, because it can be defined as an expected value, but only over the current period. So we could consider random information that occurs between now and k+1. It depends on the context whether you do this or not, but that's typically how it's defined. But that, I think that will become obvious when we draw this picture. So here's a picture of a decision tree. The classical decision tree uses squares to represent states. In a particular state, this is our initial state, I'm going to have some choices I can make. Let's say I've got 2. Collectively, these choices form my set of feasible decisions. So maybe I have X01 and X02. As a result of these decisions, I'm going to face some uncertainty. I'll represent that by a chance node or a circle. This is my random information. So I'll call this, this is a realization of W1. So we might say a capital capital letter for the random variable. These are two possible realizations. This would take me to my next state. And then we could have something similar down here. Your contribution to your question, the function here is a function of my state, that's 0, and a selected action. It can be defined as some expected value across this information here. Now we can keep building this tree from left to right, and we can enumerate all the actions I might take, all the uncertainty that might occur in this process. If we build it, the entire tree will tell us every state we could possibly be in, every action that we could possibly take, every realization of information that we might ever observe. So that way it's very informative. It's also typically very large. Okay. They say a picture is worth 1,000 words. Do you have anything I can clarify here? Yes.
When there is the entity, the value between the uncertainty and the state.
Between the uncertainty and what?
State, the
next state. So how do we transition perhaps from one state to the next? Right. So this, to use the notation I think I put in your sheet, I'm going to have a transition function. I call it capital S. It takes as argument my first state, my selected action, and then some information. And then this will be equal to my new state. Does that make sense?
So it did not appear in the quotation value.
Here. So now the contribution is not a function of the future state. It's only a function of my current state, my selected action, and if I'm taking expected value, this information. Although those things implicitly define the next state, so you couldn't think of it like that. Does that help? Okay, you're not convinced, I can tell, but Mike, you had a hand up.
So C is a function of CKs, yes,
A function of what?
of the CKs. Right, you're summing contributions over evidence, right?
This is a single calculation at a given epoch. I should have made this C0, 0. Yes.
Your effort starts after the arrow where we have capital X01 or with S1.
The new epoch starts with the new state. Right. So here's the first epoch. Here's the next epoch. Here's the next one after that. Yeah. So each, we talk about them as periods. Epochs mark the start of a period. And a period contains an initial state, a selected action, a realization of information, and then a transition to a new state. Good question. Okay, yes.
The two S1 states are not the same, right?
Okay, good observation. I'm glad you brought this up. I wrote them the same, so you might think they're the same, but they're actually different because the information here is different than the information here. So you can think of this as a random variable, the realization of which is a function of the action I choose and the information that is observed. Yeah, good question. Anything else? Yes.
I just want to make sure that I got it correctly. So the capital W stands for the actual random variable, the stochastic random variable, and the small w stand for the particular realization of this rendering.
Exactly,
All right.
exactly. Yeah. Okay, good questions. If this isn't making sense to you immediately, that's okay. It took me a number of years to really feel comfortable with it. And to expect you to understand it in 10 minutes is probably unrealistic. Yes.
Same as the state space representation.
So in the context of a dynamic program, a state space would be the collection or the set of all possible states I might ever observe. So if I took them all and bundled them into one set, that would be the state space. Anything else? Yes?
And the sum of the probabilities in W121, like the two probabilities, so the four.
So if I look at the probability of W1 conditional on my state and my action, these conditional probabilities should sum to 1. So that would be these two here. These two would separately sum to 1. Good question. Anything else? Okay. Where are we? I think we're moving on then to page 4. I want to give you an example of this, an example that we'll come back to later on. So this is not only an exercise in understanding model elements, but something that will help us understand a methodology in a later lecture. Okay. Example, same day delivery with heterogeneous fleets of drones and vehicles. This is by my colleague Marlon Ulmer and my dissertation advisor, Barry Thomas. Here's the problem description. A combined fleet of vehicles and drones deliver goods from a depot to customers who dynamically request service over a finite operating horizon. The vehicles operate across a road network, have unlimited capacity, and travel slowly. In contrast, drones travel quickly in straight line distances, can carry only one package, and must recharge between trips. Requests follow a known spatial temporal distribution, but their times and locations are unknown before the request is made. Requests may be accepted or rejected. Accepted requests must be serviced by a hard deadline and may be satisfied via drone or vehicle. The objective maximizes the expected number of serviced requests. Excuse me. So I've copied and pasted a picture of a state variable representation from this paper. So take a look at that. We have a legend to the right. We have vehicles, drones, we've got a depot, customers, new requests. And this is meant to illustrate a particular square node you might observe somewhere in this decision tree. Okay, here's an exercise I have for you. Let me see, how many of you have with you a laptop or something you can access a PDF file with? Many of you, good. So I'm going to assume you have the link that Fabian provided for the cloud space. Is that a yes or no? Okay. Go ahead and go there. And I've provided a PDF of this paper. Here's what I want you to do. Review section 3.3 to identify decision epochs, states, actions, information, contributions, transition function, and objective. Briefly describe these elements in words, not algebraic formalism, all right? Just write down a brief sentence. What is an action? What does a state consist of, etc. Okay, feel free to work with your neighbor. You've got a few minutes to go through this. Don't try to take a deep dive into this paper. I simply want you to glance at section 3.3 and make a note of what each of these model elements consists of. Go ahead. It should be this file. So just skip everything and go right to 3.3.
Ja, so Genau. Oder in diesem, genau. Ja. Das ist auch ja, es würde new customers oder es würde nur das ist eine Menge Sachen. Ja. Es ist halt so motiviert, dass nur einer kommt. Ja. Und dann ist halt als, wenn halt ein zweiter gleichzeitig kommt, aber in der dritten Sekunde, also die Abstände von den Decision Epochs müssen ja nicht wie bei Mikrofon gleich sein, sondern es kann so eine Decision Epoch geben, und dann gibt es so eine Decision Epoch. Je größer die voneinander weggehen, umso weniger häufig kommen Nachfragen rein. Der Anfang.
You're going to be tempted to read in depth. I want you to skim very quickly. You have 2 more minutes. You should definitely read in depth, but after the class.
I didn't see it.
Saves no actions.
Okay, I know you're still working. That's okay. We're gonna start listing answers to these prompts. So you probably have the first one or two at least. Someone tell me what defines a decision epoch in this problem? Yes,
A decision epoch is made whenever a new customer is arriving and just requests a service. So as opposed to another paradigm in MDP modeling, we're not talking about micro periods, but decision epochs or periods of different lengths depending on how frequently customers arrive.
right. The moment of a service request defines an epoch. So in that sense, the time of the request is a random variable. So we might think of this as a semi-Markov decision process in that sense. But we don't need to go into that detail. We just need to know what is it that defines the start of a period. It's the decision epoch. What defines that? It's when a customer requests service. Okay. How many epochs will there be?
The number of,
What was that, Gal?
the number of customers,
Okay, the number of customers and how many will there be?
it's random.
It's random, exactly. We don't know. So this is a very real world problem. The number of decision epochs is unknown because the number of customers, we don't know it ahead of time. What is a state in this example? This is a long one. Yes. Did you- A little louder, please. Can you say it louder?
The customers request that we know, but still not valid,
Okay,
and the number of vehicles and loans that's still available.
yes, yes, those are elements of the state. I'll write down the list I collected. Yeah, this is roughly what they say in the paper. It consists of a state variable. Go back to the definition of state variable. What is it? It's everything we need to know to be able to select an action, calculate the contribution, and make a transition. So presumably, we need to know all of these things to do those things. At this point, let me say that this is pretty complex. The classical introductory Markov decision process example would be much, much simpler, but this is a workshop on transportation, and nothing in transportation is simple as far as I can tell. Question?
And you're always saying like everything we need to know, but I don't like the formulation because like you can't know everything, so.
So what I mean is, let me mute this. So for example, I have this set of feasible actions. I have to be able to define that somehow.
Yeah.
So if whatever I need to know to define this, whatever I need to know to then calculate my contribution, I'm gonna have to have that information in my state somewhere. And then eventually when I make that transition, if I need to know something to do that, it's gonna have to be in the state variable. So that's different than saying that I know something about the future, which I think is what you meant.
Yeah.
Okay. Yes,
State variable, we also need the installation of the deadline.
information of what?
Deadline.
Deadline. Yeah,
Yeah.
well, I think I probably missed that. Yeah, that's probably true. Sorry, I can't hear you up here. Mhm. Okay. We probably could go into a lot more depth on what each of these is, or maybe add some others. That's fine. We'll leave the list short for now. Let's move on to actions. What is an action in this problem? Yes.
An action is whether to accept or reject an order, a request, which then, if it is accepted, becomes an order. And if we decide to accept an order, we have to further decide whether it is assigned to a vehicle or to a drone.
I think that's right. Anything to add?
What was the routing?
What about the routing? I made a note, determine the resulting routing plan or planned time of arrival. I think they maintain a route plan to make sure they can meet the deadline that one of you mentioned a moment ago. Okay. What is information in this problem? Mike, you have a question?
When did they determine dispatch?
Dispatch of what?
Here, at some point they got to tell the cargo.
I'd have to dive into the paper. I don't know off the top of my head. No.
Yeah, okay.
I would presume that this is baked into the route plan somehow.
Yeah.
That must be the case. Epics are triggered by customer requests, so vehicle movement must be a result of the action you take, which is in part updating this route plan. Okay, what is information in this problem? Yes,
Do you mean a new transition or
transition can be a function of information, but what were you going to say?
like the new customer request is reviewed?
Exactly. What is the contribution function? Yes.
Understanding the difference between the information and
Good question. So what is the difference between the information I wrote here and the element of the state variable that looks very similar. Yeah,
Well, well, here the information arrives and then there is a function to put this information into the new state of the next decision.
good. So if this is my current state, I've selected some action. And now I observe some information. This was what I knew previously. This is something new. So this is customers I know about now. This is a new customer request that arrives in the future. Good question. So the contribution function is what?
Sorry, just one step back. I think that there's so updating the route plan is also part of the decision.
Yes,
How to update it, so the
right. They must have some mechanism in the paper that does this. And I would have to go read and see what it is.
Then
Say it a little louder, Tuche.
change the past actions. Then you would look them up.
I think the route plan is about potential moves in the future. So I'm not implying that when I make an update, I might do something in hindsight. This is about updating future movement of the vehicles and drones.
But you're not changing the routing on existing.
I suspect you probably can, as long as that the deadlines for accepted customer requests can still be met. So to find out the answer to this, I think we could go into some of their illustrative examples. I think they'll have a route plan. They may change it, but I suspect any change respects the deadlines of customers already accepted for service. Yeah, this is complex. So what is a contribution in this case?
Since the objective is to maximize the expected number of service requests, single stage contribution would be binary. So if we do accept a customer, we can just evaluate the value of accepting a customer by 1. And if we do not so, we will reject him and then the contribution is 0.
So 1 or 0, that's it. In this example, the contribution function is not an expectation across future information. It's only a function of the action. Do I accept or reject? Okay, then the transition function does what? I wrote down specific updates depend on the selected action. In general, updated planned routes, arrival times, and drone availabilities, update the set of not loaded customers, update the time and location of the new request. So essentially, we're going to take every element of our state variable and update it with the consequences of our action and whatever new information we receive. Yes.
Isn't that mixing up a bit with the action? Because like, I don't know, in the paper, for example, the update of the route is like learned or also like a heuristic or something. And then I would argue that maybe it's also just transition function.
I think I'd have to dive into the paper to really dissect that. I'm not sure off the top of my head. However, the author of this paper will be here in a couple of days, and I suggest you all take this paper to him, underlined and highlighted, and say, I have some questions for you, Mr. Ulmer. Can you explain what you were thinking here? And he will be happy to talk to you all day, and if you buy him enough alcohol, probably all night. This is true, I know this. Finally, this brings us to the objective, which is to do what? Yes.
Maximize the expected rewards.
Right. Maximize the expected sum of the contributions. Okay, I'll just do a shorthand like this. What is my decision variable? This is a quiz. Every optimization problem consists of objective constraints and decision variables. What's my decision variable here? The policy, right? I've got a space of policies, capital pi. I'm maximizing over this space of policies. So it's each policy is a sequence of functions. Okay, guys, you did it. That's your first introduction, perhaps, for some of you, to what a Markov decision process is. Raise your hand if you feel thoroughly confused. I was expecting a lot of hands to go up. But Mike raised his hand, I think. He's a stochastic programmer. It's okay. Okay. What time are we going on break? We have some time still, right? Fabian?
10 minutes again.
Okay. 10 minutes? 15. Yes. Okay, which part? The policy space? So remember that a policy is a sequence of functions. So every element of this capital pi looks like this. And I have to choose one of these functions as the maximizer for my expected sum of contributions. So it's just like choosing a decision vector, say, in a linear program, except that instead of a vector of scalar values, I have a sequence of functions. Yes.
Decision in linear programs are often like everything possible. So all arcs are connected, all vehicles are included, but here we limit that by the decision strategies we are setting at the beginning. Or
We limited by the model elements we've defined. So what is a state? What is an action? What is information? And how do we transition? Those things define the space of states you could have and the actions that you could select in those states, and consequently they define the policies that could be constructed from them.
okay, so also this set is then extremely big.
Very big. There are continuous elements of this state variable. Time is a continuous element in this particular problem. Location, I think, is also continuous, although maybe they have it on some grid. I can't remember. So this could be infinite, which is another challenge that we face. Okay, I want to transition to the next topic, recognizing that you have and will continue to have questions about this example. That's okay. The purpose of today is not to fully understand everything at the end of the day. It's to help you know where to go to learn more when you decide that it's time to learn more. Otherwise, you're not sure where to start. So turn the page with me to section number 2. Thank you. Essential theory. Thank you. There is a lot of rich theoretical work in Markov decision processes. We're going to skip over almost all of that. Don't anyone send this video to Demetrius Bertsikas or Martin Putterman, please. They have exceptional textbooks on theory, and I highly recommend them. The purpose of today is not so much a theoretical deep dive, but to just understand the basics. So I'm going to give you the most fundamental result in all of dynamic programming. Okay, A stochastic dynamic program asks us to identify a policy with the following value. You know this already because we've written it down, but I want you to write it again. We're going to maximize over the space of policies. And we want to choose a policy with the maximum expected sum of contributions. Most market decision processes can be written like this, generically. This hides all the complexity, but it is a succinct statement of the problem. An exact solution method identifies an optimal policy in recursive fashion. We show that the value of any policy can be calculated recursively. A backwards solution method for an optimal policy then follows. The expected total contribution from state SK, if we follow policy pi, let's write it like this. So if you're thinking of the decision tree, I want to write this objective, but not from the initial state, but from some generic state SK. Let's abbreviate this with this F notation. And instead of maximizing over policies, I'm going to fix a policy pi. I want to know what is the value of that pi from some state SK forward. Take a moment to write that down. Notice that FK looks a lot like the objective, except I've fixed a particular policy pi, so there's no maximization. And I'm not starting at S0, I'm starting at SK. Yes.
Shouldn't be the K subscript replaced by K prime?
Yes. So make all these primes, thank you. Good catch. Yes.
The expectation that you have there, where is the uncertainty in the argument?
Good question. So another way to phrase your question is, what am I taking the expected value with respect to? What is the randomness in either of these expressions? Draw up.
It's the escape because we contain the future random.
Right. We don't know what the future state variables will be. So this is expectation across trajectories of state variables from now to the end of the horizon. But that's kind of abstract. What does the randomness really depend on? It's the random information. So that the transition function captures the random information states. It's also a function of the actions we choose. Although here the actions are fixed. So it's not a function there. That's why I drew the decision tree earlier. Because if you write it like this, it hides all of that. If we draw out the squares and the circles and the arrows, then we can more clearly see that there's an evolution of the state variable and it's a function of this random information.
Just to be sure that I'm understanding, that I can replace that expectation term by a sum of like a weighted sum of a bunch of steps that each at different sequences of S0, S1, S2.
Yes, I mean, that's the definition of expectation. So a weighted sum of values. So if we took every possible trajectory of states and the probability of observing this, and we took the rewards across those trajectories and multiplied by the probabilities, that will be exactly this. That's right. Good. Okay, are you ready for the unveiling here? We can show that fk pi can be calculated recursively as this. This is the first of two results I'll show you. We can take this expected summation and write it down as the value of what happens now, so I'll put now here, plus what happens in the future, or the expected future. If you stare at the decision tree picture you drew long enough, this will start to fall out of the structure of that. That you can start at the end and work backwards one stage at a time and just capture all future stages in this recursive term. Okay. Are we ready for break yet?
Why are we using B instead of F now?
Say it again.
Why are we using B instead of F now?
Well, I want to distinguish between V and F. So this is a different function. This is going to be called a value function for a policy. They have very different forms. The result, if you look at proposition 1 on your paper, is that these two are equal. So that's proposition 1. Let me take 5 more minutes and give you the main result. Okay. The value of an optimal policy from state SK is Fk star of Sk. So I'm going to write this. Well, hang on. We'll write that in a moment. We can show that Fk star may be calculated recursively as a value function that looks similar to this. So let me write down over here. So what theorem 1 does is it recognizes that for any policy we can go between these two forms. And then it says, let's apply that to every possible policy. And we can find the value of an optimal policy through this recursive form, which we call the value function. Okay, during break, I want you to use some osmosis and let this settle in. And we will do a short example of how to apply this in backwards fashion when we return. So I think we have a break from now until 10:45. Sound good? Okay, see you in 30 minutes.